Okay, 2 years later.
First of all, I want to pause and talk about what that first line means. Again, I know I'm being very basic, but I really I don't know, I felt like it's really important to me that you guys know what a sampling distribution is so that you don't see those words and just go off over that. Okay, so to remind you, a sampling distribution is what you get when you take all possible samples of the same size from a population and plot that on a dot plot or histogram. And then the center of that would be your best guess of what the population parameter would be. So the sample information should give you a pretty good estimate of the population information. That's what this whole class is about. There are two different ones that we focus on. The first one is going to be proportions, which is like your M&M situation. So we're going to talk about the M&Ms again today. So when I say sampling distribution of a sample proportion, P hat, I want you to think about your little cup of M&Ms. Okay, pretending that there's little cups of M&Ms to cover every single possible sample of size 20, which is impossible, but think about it, like Scrooge McDuck, you know, stacks and stacks and stacks of M&Ms, you know who he is? He like swims in his money, you know, just pretend you're like swimming in M&Ms. Okay, so you take all possible samples of size 20, which we could never do, but I said that, you know, you could do it with a simulation or like that applet I had yesterday. Then graph that, and I want you to think about what that would look like, where the center of that would be. You guys should already have an idea of where the center of that should be. And the spread, we talked about that yesterday on the yellow sheet. I kind of gave you a hint about that formula. There's a formula for it. Okay, so if we can do that, and we're gonna do the M&Ms example and then a different example just to make sure that I'm not hyper focused on one thing, because, you know, type A, it's possible. Anyway, okay. Now, the shape. Do you remember yesterday how I said there was foreshadowing on my applet? I had a really skewed population. What were the shapes of the sampling distributions underneath? Normal. Okay, normal. Okay, now that's not always going to be the case. There's a condition of whether or not it's normal. I want you guys to flip back in your extremely well organized notebook. Do 6.3b. Flip back to 6.3b. Okay, unless you have one of those notebooks that you gotta flip it end to end, then just look at mine. Okay. Now, if I can remind you, so first of all, this particular situation is dealing with proportions. I want to remind you today we're dealing with proportions. When you think about M&Ms and the proportion of blue in your little cup, and he's saying if the sample size times P, which is the proportion, in our case for the M&Ms, that would be 0.25, is greater than or equal to 10, and the sample size times 1 minus P is greater than or equal to 10, then this is a binomial situation, but we're going to say the sampling distribution is normal enough to use normativity. The large counts condition applies to sampling distributions also. Okay, do you guys remember the paper I showed you with the graphs of NSC? It was like the ones in the middle were normal and the ones at the bottom were normal. And as the proportion got more 50-50, and as the sample size got bigger, they all got to be more normal. Do you remember that? Okay. You can trust me that we did this, or you can go by the formula, but this large counts condition applies to binomials, but it also applies to sampling distributions. Okay, so this is
what will give you the ability to use normal CDF, which is foreshadowing, by the way. Okay, so we're gonna write for shape. First, and always check the graph. The problem is a lot of times they don't give you a graph. What was the shape of our M&M's graph? It should have been kind of roughly symmetric. I mean, it's not perfect because, you know, there's only 24 samples on there, but it should have been, it's not bad. Can we go with that being roughly symmetric? The question is whether or not it's normal enough. And guess what we're going to do in example 1? Figure out if it's normal enough. Okay, so check the graph first, because they could be anything. They could be skewed, they could be uniform. However, you really want them to be normal because, again, you want to use normal CDF. Okay, so check the graph first. Then, if you don't have the graph, and you should still do this, check the large counts condition. Okay, and because the reason is you look at the graph and you're like, not sure. Is that normal? Is it normal enough? It looks kind of bell-shaped-y, but is it good enough is the question. Okay, so to remind you, the large counts condition is n times p is greater than or equal to 10, and n times 1 minus p is greater than or equal to 10. Okay, if you get yes for both of those, then it's normal. Okay, and if it's no, and you don't have a graph, put not normal, because you don't know what shape it is. All you know is it's something else. Does that make sense? Okay, so you check the graph. Sometimes you can tell it's really skewed. Sometimes you can tell like exactly what it is. Check the large counts condition to see if it's normal. If yes, say normal. If no, say not normal because you don't know what it is. Okay, center. This is where you need your yellow sheet. So where do I want to write this? Not enough room. Okay. Okay, now don't put this away. We still have more things we're gonna write on it. But before we write anything about the center, I need to go over this statement again. It took me 2 days to teach this little statement. Monday and Tuesday, I spent teaching this equals this. And it's just on there, like you get to just assume it. But I spent a really long time trying to build that up. Okay, so let's go over that again. This is saying the mean of the graph that has all of the sample proportions on it. Okay, so the mean of the graph that has all of the sample proportions on it should be equal to the population parameter. Okay, so what I'm saying is the center of your M&M's graph, which should have been about 0.25, should be 0.25. Can we say that any of that again? the center of your M&M dot plot should be 0.25. Is it gonna be perfect? No, it's okay. But it should be the same as a population parameter. And why? Because it's an unbiased estimate. It took me 2 whole days to prove to you that it was okay to estimate with proportion. Okay. Now this guy is new, but we talked about him yesterday, that n in a denominator situation, but there's a special thing with that, and we need to talk about that first. Let's go back to the center real quick. Okay, so I just summarized my 2 days worth of teaching right here. So there's the formula from the sheet. And what this is saying in words is the center of the p-hat sampling distribution dot plot should equal the population parameter p. Is it going to be perfect? No. How can you make it more perfect? There's 2 ways. Increase sample size and increase the number of samples. Ours was only 24, so you only got 24 dots on there. Now imagine how cool it would look if I combined first periods and fifth periods dot plot. It'd probably be better. I mean, not probably, it would be better. Okay, but for this bit, again, I just want to really make sure the center of the p-hat dot plot, so p-hat equals sample proportions of blue candies in the sample, should be the true population parameter 25%. And this is backwards stats magic, which means that I can use samples to figure out stuff about the population. Because most of the time you're not going to have this info. Otherwise, you would not do it. Like, I don't know why you would sit and count out M&Ms if you just Googled it and went like, oh, it's 25%. Okay. Now spread. There's a special thing about spread too from chapter 6. So this was your first thing from chapter 6. And there's another thing from chapter 6, which we are going to have to put something here about. Do you remember us talking about sampling without replacement? Okay, I want you to think about Mrs. Talbot sitting at her dining room table with the giant bag of M&Ms that she bought with a little glove on and her Dixie cups and putting the M&Ms into the Dixie cups. Did I replace those M&Ms before I gave them to you? Did I dump them back into the bag and then count out another 20? And then dump those back into the bag and count out it? That would be really fruitless. That would be a large waste of time. Probably not the largest waste of time of my life, I'm sure, but that would be binge watching stupid shows. But anyway, so this formula assumes independence. Was my situation independent? Me putting the M&Ms in and then setting the cup aside and then taking more M&Ms and setting the cup aside and then taking more M&Ms and setting the cup aside? Was that independent? No, sadly, because I didn't replace that. If I had poured them in every time and mixed it up and then put more in the cup, that would have been independent. I didn't do that. And neither would you, because that wouldn't make any sense. However, back in chapter 6, I taught you a cheat about how to get around the independence condition. And you have it in your notebook and it's got a giant hat drawn next to it. find your hat picture that you drew in your notebook from chapter 6. Oh, it's in the same lesson. What do you know? Read this again. This is also important to what we're learning now. If sampling is not replaced, the independence condition is not necessarily met. Good. However, some situations allow us to bypass the independence condition. Visualize all of the students' names at VHS and a half. Okay, instead, visualize all the M&Ms in the world. What's the probability that I select any one of those M&Ms? A tiny, tiny number, right? 1 over, well, so many, I can't even write it. Probably some kind of scientific notation. Yeah. Okay, so that M&M is gone. Now, what's the probability that I take out the next M&M? Is it equal enough-ish? For sure. And could I even get to 10% of the world's population with M&M? No. Okay, so for us to use the standard deviation formula, we need to show independence. And if we're not sampling with replacement, which we're not, we need to say that our sample size is less than 10% of our population. So we're going to write 10% condition. If your sample size is less than 10% of the population, the distribution can be, or you can say, and you can assume independence, which is what this is saying. Okay, so let's reword this for chapter 7. Okay, now just write, I don't know if you guys are writing ahead, but just write to here for the moment. Do you feel like I'm missing a colon there? I feel like it needs a colon. Okay, what I want you to do is take your yellow sheet, go to this box and put comma. If 10% condition is met. Now, this will be something that is, you're going to do so many times that it's just going to become habitual and you won't need it on your sheet. But right now, I think it will be really helpful for you to have it on your sheet. And the reason is because I'm a little scared. So let me tell you my fear. I'm a little bit scared that you're going to mix up the large cap condition and the 10% condition. And it doesn't help that they both have 10s in them. So I was hoping if we put this on here and you had it on your yellow sheet for your test, you'd be like, okay, standard deviation specifically is the 10% condition, because that needs independence for that formula to actually produce the correct number. But the shape is what the large counts condition. The shape is n times p is greater than or equal to 10, n times 1 minus p is greater than or equal to 10. Red requires independence, which is this. Also, another note, just for those of us that are particular, the large counts condition is greater than or equal to. The 10% condition is strictly less than without the or equal to. Just, I'm gonna try to never trick you with that. Like, I'm gonna try to never give you something that doesn't work very obviously, because I'm not a jerk. But I did just want to be very clear about it. Okay. So scooch this over. Okay, then set this guy up, and we're going to apply all of these things to the M&M's graph. Okay. Now there's something very important that I need to mention in this one, and we're gonna go play with the applet again, just because I'm the giant, I don't know, I care a lot. And after this, I only have one more thing to do and then we're done, so I'm just gonna make sure to do a good job. But I said, this is very subtle, but I said describe the sampling distribution. I did not say describe the approximate sampling distribution. I'm not saying describe your graph from your class. I'm saying fantasize, imagine that it's perfect with all possible samples, like the ones from the applet. What would that look like? And so we're gonna do it in the applet so I can prove to you that I'm not making stuff up over here. But, okay, so ours might be a little different because it's our only 24 samples from our class, but okay. So shape, first thing I told you to do was check the graph. Is there a possibility that this is normal? Yeah, it doesn't look ridiculous. So I'm going to give it a chance. I'm going to check the large counts condition. Okay, I am not going to write large counts condition on every single one of my math problems. I'm doing it now because I'm trying to make sure you guys know the difference between that and the 10% one. Okay, large counts condition says n times p is greater than or equal to 10. What is n in our problem for the M&Ms, right? 20. And what is p? 0.25, great. Okay. This is sad. But that's okay, because I wasn't going to attempt to find the probability of the emphasis anyway, I was just asked to describe. So what shape is it then? Let's take a look at the applet to decide, but we don't really, yeah, for you guys, if you were doing this on a test, I don't care what, if you find the shape, just say not normal. But we're going to try to attempt to find the shape on the applet, but you guys do not need to do that. If this doesn't work, you say not normal, you move on with life. Okay, now the center. The mean of the sampling distribution should be equal to P, 0.25. Is it? Kinda. Ours, I mean, that's not ours, that's fifth period. And theirs is worse, by the way, yours is better. I know I'm on the video, sorry, fifth period, theirs just didn't come out. It's really my fault because I was the one that put the M&Ms in the things, but I did it randomly, so what are you gonna do? Okay, now the spread. Now we know that I violated the independence condition. I had to, otherwise it wouldn't work, but I'm pretty confident in this statement. You guys pretty confident in that statement? So pretty sure there's more than 200 M&Ms out there. Okay, so that means I can use the formula. Standard deviation of my graph is 0.25. 1 minus 0.25 over 20. Zero 0.097. And this is not, you might think that that's a weird decimal, but that shouldn't be that weird considering the center was 0.25. So when you're dealing with proportions, they're going to be decimals and the standard deviations are hopefully going to be small because you're counting by decimals on each side. Okay, so just put your pencil down and chill for a second. We're going to just take a look at the CPM applet, which I did not bring up this morning, but that's okay because I'm sure it's in my. Why? Why like this? Guys, are you leaving me right now? Mentally? Thank you. Okay, so there's one I made that looks like, possibly one from one of your classes. Not exactly the same. But I'm not really, I just wanted to throw that up there. I'm not really interested in that. I'm interested in what it looks like when it's perfect. And this tool, the simulator won't make it perfect, but what I can do is put a lot more samples. Okay, and so I want to do two things. This e-tool is actually really cool. I give CPM a hard time, but this particular one is cool. So first of all, do you notice that it's not really normal? And this tool will allow me to put the normal curve over top. You can kind of see the skew. And then it also allows me to show the summary statistics. Okay, so take a look at the standard deviation. Okay, what was our standard deviation? Yeah, and this is just a little bit off because they used 524 samples to make this graph. It's not perfect, but it's pretty darn close. Backward stacks magic. Okay, so let's go back up and revise and just put right skewed. I would, again, never expect you to do that on a test or quiz or something. I would just expect you to put not normal because you would not have this beautiful thing. I would have guessed that off of our dot plot, actually. Okay, any questions about this one? Checking the shape, center and spread. Shape is large counts condition, yes or no, basically. Center is on your yellow sheet, spread is on your yellow sheet, but making sure that you're checking for that independence condition for 10%. Also, I want to make sure you guys understand that I'm working in the top, these two boxes today. And the P hat is what will tell you like what you're working on in that particular problem. Because the thing is, they're going to put a bunch of them together. They're not always going to be proportions. So we need to be careful that you guys know where you're supposed to look. Okay. All right, we are down to the last thing, everybody. If you could send a representative over to grab a basket if you don't have one, that'd be great.
We did not one word.
Mhm. No, there's also gonna be a normal CDF. It's just gonna be like right to here.
Okay.
I was thinking on that. How would
Now take everything. Go ahead here.
Oh, Callie, actually, I was gonna write the interpretation sentence for spread over here too, but I don't think it's gonna make it any longer.
Yeah, I should be okay.
Okay.
There's people that start like going and choosing that. You're not really tired. It's like I'm getting no more. Not like you think you do something. People that are.
Well, I think, okay. No, I know you want. Oh, no, this shut up, you guys are. Oh. Really know.
That works. You'll at least get.
I don't want to send any, I don't want to send advice from my head.
Whoa. They're gonna agree one. Yeah.
Okay, you guys ready? No? Okay, so. I've set this up. Kind of, it looks small, but, I'm probably gonna take up here, just so you know. So you might have to cram. So I'm going to put the center here, which is usually just one number, but I'm going to do the interpretation sentence. And then for spread, I'm going to do the interpretation sentence, just because I want you to have a spot where you can see those. They're not really, that shocking. They're exactly the same thing as before, like over random samples, average something, and then over random samples, something typically varies from the, so. There, I just want to make sure you have them. And this is the only spot that will do them probably. I can't remember, but, okay. So, I sat down, I'm taking a test, this is an FRQ. Suppose that 35% of all first-year college students attend college within 50 miles of home. Find the probability that a random sample of 1,500, that's pretty big, students will give a result within plus or minus 2% of the true value. Okay. So, Mrs. Talbot's taking a test. This is what my mind would do. I would say, okay, shape. I have no graph. The only thing I can check is the large counts condition. I wouldn't even write this if I was doing a test, but because, we're doing this together, I just want to. Okay. So N times P is greater than or equal to 10. And N times 1 minus P is greater than or equal to 10. Okay, so Mrs. Talbot's coming in, she sat down, she said, find the shape. I found that it was normal, which is a relief, because that would be the only way I would know how to find the probability, because I clearly read the whole problem first. And didn't just jump into it and saw that in the problem, it said something about finding the probability, in which I need to use some kind of cumulative density function. Your question is, are we gonna use binomial and geometric in this chapter? No, it's normal and not. Okay, so any questions about the shape? Okay, sadly, if one of these were not greater than or equal to 10, I would not be able to move on with the problem. I'd have to stop there. That's never gonna happen. I'm not gonna give you a whole FRQ where you do A, find the shape, and then it's not normal and you can't keep going. If that happens, it's a typo, I promise you. Okay, center. I get my yellow sheet, which I don't because I have the yellow sheet pretty much memorized because I'm a giant nerd. I would say, okay, I'm working with one population of proportions. So my center is going to be P. mean of my dot plot should be at 0.35. Okay, any questions about that? Now, it's not done because we're going to write the sentence, so I'm gonna try to cram that in. Oh, no. I need to move the spread word down. Anyway, it's fine. Oh, God. Why did I pick a context that is so long? Okay, do you need to interpret every single time? No, you only interpret if it says interpret. I just wanted you to have an example so you could look back on it. I don't know if you interpret very often even. Is this sentence shocking to you? Like, I feel like you kind of could have come up with it on your own anyway, but okay. Spread. Okay, so I go to my yellow sheet and I say, okay, this is my spread formula if the 10% condition is met. I need to check that first. So 'okay, so think about what we wrote. N equals 1,500 is less than 10% of all first-year college students. Do you feel confident that there's more than 15,000 first-year college students everywhere? Yes. Yes. There's lots of first-year college students. You're a liar, Mrs. Talbot. Giant, giant liar pants. Okay, so since that works, the standard deviation of my dot plot should be square root of 0.35, 1 minus 0.35 over 1,500, which is something. 0.012. Do you guys get anyone else get 0.012? Okay. And is that a weird number? Should I be worried? No, because the center of the graph's at 0.35. So the fact that you're going by 0.01s is actually a really good thing. Why is this so small? 1,500 sample size is huge. Great job. Okay. Not done, not done. We didn't finish it. What did we forget to do? Uh-huh. The last sentence of the problem says, find the probability that a random sample of 1,500 students will give a result within plus or minus 2% of the true value. Okay, don't worry. It's just one line. It's just a normal CDF. It's no big deal. Okay, however, so put P parenthesis. Okay, now this is the only part that's hard in this problem, and that's because we haven't done this plus or minus business before. But what is the true value? 35%. Okay, so what numbers are within plus or minus 2% of 35%? You're gonna just write it. I'm like three. What numbers are within 33 and 37? Okay. That's wrong. That's wrong, but you can fix it by doing that. That would have been rough on normal CDF. Low. High. What's the mean? 0.35. What's the standard deviation? Okay, the last thing I want to say for the period, actually, I'm done after this. I want to say that because you wrote proper random variable notation, this is what this is, although it should be zero in front of, so my bug is fine, I'm living, look at me, totally accepting the fact that there's not zero there, doing it, not at all upset about it at all. But this is a proper random variable notation. This gives you your low. It gives you your high, you stated your mean, and you stated your standard deviation. You do not need to label normal CDF that, because you already stated all that stuff earlier. So on these problems, you can ignore the labeling. It's probably just best to make yourself do it, but you don't have to. Okay, that's it.